Okay, I am recording the class, so this way you'll be able to view it later if you wish. And anybody who did not actually able to attend, they can actually do it as well. If you do have a mic, I would ask to mute it. And then if you have a question, just raise your hand and I'll pause and you can unmute it to ask your question. This way, everybody doesn't have to hear all the stuff going on in the background, including even at my house. So. All right, tonight we're going to be looking at the beginnings of Chapter 11. I did receive most of your tests. If you have not sent your test in already, please do so as soon as you possibly can. If there's some other extenuating circumstance on why you can't turn your test in, please email me and let me know. I know there's a lot of things going on, so there's people who are working way more hours now than they ever have in the past, and there's some people who are sitting at home all day now too. So if there's any situations going on that I can help you with that's impacting your schoolwork, and we will work to make sure that we can do as much as possible for you. On my website, you will see information for XYZ homework. It is going to be the way we're going to be doing the testing for Chapter 11, and then Chapter 10 and 12, and then the final exam as well, because we're not coming back for the rest of the school year. So do make sure you look on my website and sign up for that. And this way you can get access to those as well. The other nice thing about that site is there will be homework assignments built into it too. You're not collecting the homeworks. I'm not going to check the homeworks, but it does give you instant feedback on those. And I would practice some of them because at least they'll give you some information about how they're looking at for the answers to be put in and those things as well. I do have the ability to look at all the tests afterwards. So even if it marks something wrong, I do have the ability to give you credit for it if it was something that I looked at as being correct. I have a review test for the Chapter 11 and a review test for the other ones as well, just when we go to do them. So just like any other test, I'll have the review test built in for it, so you can practice before you actually. All right, so we're going to start looking at Chapter 11. 11.1 is sequences. So sequences and series are the two things we're going to look at tonight. A sequence is basically just a list of numbers. So it's can be done. We can have a rule for it, or it can literally just be a list of numbers or a list of values. We're only going to be looking at ones with numbers, obviously, because we're going to do some calculations with it. So the couple different ways that you're going to see sequences written, the notations are very important. The first one is you'll see it as a set. So this is listing every one. If you see the three little dots, that means that pattern is going to continue until infinity. If you see three little dots and then a number at the end, that pattern would continue until that number at the end goes. If you just see a little pair with a function in it, that means that function will generate the actual values. You also can see that there's nothing there. It's designed to go all the way to infinity. If there's an n1 and an infinity there, that means that's only going to go until those values occur. So this way we actually can see which values it's going to go to. And you can actually have it stop at something other than infinity. So we can look at a couple examples of it. The first one there, we have n over n plus 1. So we can see the actual function right there. And these are the values that would be produced from it. So it's a couple different ways that we can actually write the same exact thing. This is just another one, and then those would be the values that we produce. So you can see sometimes we have series that don't repeat or that are all positive numbers, and sometimes we have alternating series where the values are going to actually change. The signs are going to change from negative to positive. There's a couple other examples. We can have square roots in them. You can have trig functions in them. Doesn't really matter. Any sequence is going to have those values, and it's every number that's produced after that point. They don't have to produce whole numbers. They don't have to produce even rational functions. It can be in irrational numbers as well. All right, so let's look at a couple examples. So this is the first one we're going to look at. One of the other things that we can do is looking at a function, we want to be able to somehow come up with a sequence for that or a rule that comes up with it. So when we're looking at a set of values and we want to come up with a rule, we want to look at the top values, the bottom values, and the signs. So in this one, the one thing we're going to notice on this one is that the signs switch. So I have positive, and then a negative, positive, then a negative, and then the next one would be positive and then negative. So whenever we're doing positives and negatives, you're always going to have -1 raised to something. So I know I'm going to have the -1 raised to some power. The question is what is that power going to be? If I want the first one to be negative, it would just be n, because that means any odd numbers are going to be negative, and the first number 1 is negative, number 3 is negative, so that would be that way. But in this case, I want the even ones to be negative. So to do that, I'm just going to do n plus 1. And what that does is it shifts it over 1. So when I plug in the first value, that'd make it 2, and that'd be a positive. When I do 2, 2 plus 1 is 3, and that would be a negative. So that gives me a negative value every one that's going to be on the positive ones, or on the odd ones, I should say. We also could have done n minus 1. It would have done the exact same thing. N plus 1 and n minus 1, and this negative sign gives you the same answer.
I have a question. Can you hear me?
Yes.
Okay. Is the first value, like 3/5, would that n be 0 or would that n be 1?
It depends on how the sequence is set up. Most times it's 1.
Okay.
So unless they tell you that we're looking at it starting at 0, you're going to assume the first one's 1. So now we want to look at the top numbers. So we're going 3, 4, 5, 6, 7. So if the first one, and this actually is very important with the question you just asked, if the first one is 1, how would I get 3? So to do that, I would add 2. So my top fraction here is going to be n plus 2. And then 1 plus 2 is 3, 2 plus 2 is 4, so on and so forth. The bottom, notice it's going to be, there are multiples of this one. So this one's 5, then 25, then 125. And if you look at that, those are actually all powers of 5. So this is going to be 5, and if the first one is 1, 5 to the first power is 1, 5 to the second power is 2, or 25. So that's going to be 5 to the n power there. So that would be the rule for this sequence. Any questions on that one? So a couple other sequences that we have. Some sequences just really don't have any actual rules attached to them. So if we want to look at the sequence of the world's population, we can give that as a list of values all the way from beginning time when we actually started keeping population data, or till today. But the numbers wouldn't be, there wouldn't be a formula that could create them. That would be completely and utterly accurate. Another one, if we let n, or the nth decimal place of the digit e. E, just like pi, is irrational. It never repeats. So there's no rule for me to be able to come up with those values, but that's still a sequence. The most famous of these is the Fibonacci sequence. Fibonacci sequence actually has a rule, but it's recursive, which means you need to know the ones previous to it before then. Hold on 1 second. What's up, Mergen? I see you in chat, so. Hold on 1 second. All right, I'm gonna keep going, and then I'll catch him up afterwards. Um, so the Fibonacci sequences we're talking about is a recursive function, which means that you need to know the previous values to that function before you can do it. So in the Fibonacci sequence, we need the two previous values. That's why they give you the first and the second one, which is the 1 and the 1. And then we use those two to find the third one, and then we use the second and third one to find the fourth one, and so on and so forth. So that's what's known as a recursive function. So we can write an equation for it, but it uses stuff that's actually in the function to begin with. All right, so when we're starting to look at series and sequences, or sequences now and series after this, the one thing we want to look at though is we have to do calculations with it. What we really want to know is, does the sequence actually go to a limit, or is there a value that the series goes to as it goes to infinity? And same thing, if it doesn't, then it diverges. If it goes to a limit, it converges to that limit. So when we start looking at that one that was n over n plus 1, we can start seeing as the values get higher and higher, those numbers get closer and closer to 1. And this is one way to look at it. And then we have the graphic way over here on the table. You can start seeing it's starting to get closer and closer to that line that's at 1. So this function actually is a limit. The limit of this one is actually 1. So we can actually start looking at that. As we stall it out, you get 1 minus the n over n plus 1 gives you that. So the bigger and bigger we make the number, so this function here is in essence getting closer and closer to 0. So that's why it ends up becoming 1, because 1 minus 0 is just 1. Sometimes our sequences jump up and down. That's fine. But as we go further and further out in the list, it does get closer and closer to a specific value. So the limits can still exist. It doesn't mean that the value doesn't get higher than that or lower than that. It actually, we're looking as it goes further and further out to infinity. So it has a limit. If every value is less than the value, like it's larger than the value that we started off with, but the differences are getting smaller and smaller, and that's where the limit's going. So the graphic way to do it. So we can see that as it's going further and further, this is value right here. Those lines are getting closer and closer together. So it's basically squeezing that value down until it gets to the actual limit. So when we're starting to look for the limits of sequences, we want to look at some of the rules that are attached to them. So this way it makes it a little bit easier to deal with, because I don't have to look at just the whole function. I can break that function apart. So we can look at one plus the limit of the other one. If we have subtraction, we can split it up again. Any constants I can just pull out. If it's a limit of a constant, it just goes to that constant. If I have multiplication, I can split up multiplication. If I have division, I can split the division up. And if it has a power, I can actually split the power up out as well. The squeeze theorem is one of the things we're going to look at when we look at some of the functions. Sometimes I can't figure out exactly what the function is, but if I look at a function that's bigger than it and bigger than smaller than it, they will actually squeeze together and says, okay, well, if those go to a specific value, then the one in between them has to also go to a specific value. So those two functions, one's always going to be bigger than the other one's always going to be smaller. So it goes to that value in the middle. So that will help us find those limits sometimes. All right, so let's look at example number 4 and figure out if we could find the limit of this one. So if you remember back to when you did Calc 1, one of the strategies that we used to find limits was we would divide everything by the variable. Because if what we want is we want the top piece to be a 1, and we want the denominator to be the thing that's actually going to go to a value. Because that allows us to do some calculations there. So if I take this one and I divide everything by n, it's going to become 1. And then I have 1 plus 1 over n. Now I only have one n that I'm going to look at my limit to. So if I'm looking at as the limit of this, as n goes to infinity, horrible infinity, the 1 is going to go to 1, that's going to go to 1, and then 1 over n goes to 0. So the function goes to 1. So the limit of this is 1. So that's one of the strategies that we had, and that's the same strategy that you learned in Calc 1 when you're doing beginnings of derivatives at the very beginning when you're doing limits. If we look at this one, we're going to actually use the same strategy to it. However, on this one, because I have the square root in it, I'm not going to be able to divide just by n inside the square root. So I have to bring other stuff into it. So if I take this one and I divide them all by n. Now, in the square root, if I'm dividing the square root by n, inside the square root, I'm actually going to divide by n squared. So the top becomes 1. The bottom, I have 10 over n squared plus 1 over. So my top's going to go to 1, and my bottom is going to actually go to the square root of 0. So as the bottom's getting infinitely small, my fraction actually is going to infinity. So this sequence diverges because the limit actually goes to infinity.
Tony,
Yes.
you don't divide the top by n squared,
No,
so
because
you have n.
I'm dividing everything by n. The only reason I'm dividing the bottom by n squared is because I'm putting the n that I was dividing inside the square root.
Okay, I get it. So the top part is still just n. The
Yep.
numerator is still just n. Okay.
Yep.
Thank you.
No problem. All right, let's look at this one. Now, on this one, there's no easy way to do ln of n, so we're actually going to lose the L'Hopital's rule and then do the derivative of both of them. So the derivative of ln of x, or ln of n, is 1 over n. And the derivative of n is 1. So if we look at that, that goes to 0 over 1. So my limit is 0. So we can use any rules we want that works with limits to solve these out. And the L'Hopital's rule is one of those that we can actually use. Now this one, if you can't see it, I'll rewrite it. So I have a to the n equals negative 1 to the nth power. So this one isn't really a rule that it's on a function because it's just negative 1 to the nth power. This one's one that if we look at the values, it actually makes my life a lot easier. So my first one's going to be negative 1, then 1, then negative 1, then 1. And that pattern is going to continue to go. So the question is, does this one converge or diverge. It only converges if it goes to one value. Since this one jumps between two values, this one diverges because it doesn't actually go to a single value, even though it only goes to -1 and +1. It's not a single value, so this one also diverges. So now, this one, I have the limit as n goes to infinity of -1 to the n over n. As we're going to infinity, we actually can look at the absolute value of that function because I've got some other information there with it. So I've got the n and stuff too. So we can take the absolute value of this function. Next thing on my Amazon order is a new pen to write on my screen. So I end up getting 1 over n. Now as that's going, the n's going to infinity, that's getting infinitely small. So this is going to 0. So the limit exists for this one, and it's going to 0. All right, so one of the things, the other thing that we want to look at is, it says this sequence is decreasing. So why is the sequence decreasing? And one slide right here. So the thing we want to, one of the things we want to figure out is if the sequence is always increasing or if it's always decreasing, it's called monotonic. We can have a series that is increasing all the way and still have a limit. We can have a series that is decreasing and still have a limit. We can have a series that is increasing that doesn't have a limit. And we can have a series that is decreasing that doesn't have a limit. So, however, if it's only going in one direction, that gives us some information about it that we can actually start looking for limits. So the first thing we have to be able to figure out is the sequence increasing or decreasing? So if we look at this one here, we basically want to look at is this value right here. So it's 3 n plus 5. Is that going to always be greater than or less than, depending on which way it goes? They're telling me this one's decreasing. So, and then it'd be the n plus 1 value. Yes. What's up? Whoever just raised their hand. Okay. So when we're looking at increasing or decreasing, we're going to look at is one value is we're using the function. We're not actually going to use numbers because if I plug in numbers, then it might only be true for those couple numbers that I plugged in. So that's why we're using n and n plus 1 in this case. So then I would have 3 over n plus 5, and this one would be 3 over n plus 6. And I know if the denominator is smaller, so in this case, this denominator right here is smaller than this one. Therefore, this fraction is bigger than that one. So this function, the sequence, is always going to be decreasing. And we would do the same thing with this one. We would do this one, however, is a little more complicated because we have the n plus 1 squared in there. But we would do the same calculations and break down to figure out, is it increasing or is it going to be decreasing? Now, if a function is bounded, which means that there's no value that it's going to go higher than, or it's bounded below, it's known as a bounded sequence. So if it's bounded above and below, which means there's no value that's going to go higher than and no value that it's going to go lower than, it's a bounded sequence. That's actually important. And what's going to come into play is if we think about the sequences we were just looking at, where we had ones who were increasing only or decreasing only. If I have a series that is only increasing and I know it's bounded above and below, then there has to be a limit because it can't get outside those two values, so it's going to have to be a limit there. If it's only decreasing, same rules would apply. So knowing if a function is bounded above and below, and if it's increasing or decreasing, that's actually very important. It helps me figure out what the sequences are. So if it's both bounded and monotonic, then it has to be convergent. And we can start looking at here. I know the value doesn't go higher than there. It's only increasing, so it has to go to some limit that's below whatever the bound happens to be. Okay, that's the end of sequences. So is there any question on sequences before we go into series, which is basically just the summation of my sequences? All right, if we look at series, yes, other than the fact that my screen went away and I had to fix it. Question? All right, a series is a summation of a sequence. So a series is basically taking a sequence and adding all the values together. So as strange as it sounds, pi is a series because I can write pi as as a set of additions all the way down. Now, it's never going to repeat, so there's no rule for it, but it is something that I can actually write a series for. So we have a couple of different types of series. Series can end, or we have an infinite series which goes on forever. And we're going to do the same things we were looking at with sequences. We're going to be looking for, do they converge, do they diverge? If they converge, what is the value or what is the limit of that series? So some series, there's no way to find a value for it. So like if I was just adding up all the numbers from 1 to 100, or one, like I could figure that out. I can come up with an actual answer for all the numbers from 1 to 100. But if I wanted to find out all the numbers from 1 to infinity, there's no way for me to be able to add those numbers up. So some series, there is no sequence, or there's no limit for it, or to actually find the actual value for it. But some of them, there is. So if I add 1/2, 1/4, 1/8, those values right there, I can actually start adding those values together. So if I did 1/2, which is the first one, 1/2 plus 1/4 gives me 3/4. If I add the first three, I get 7/8. Now I'm taking this series right here and making a sequence. Now that sequence, I can then produce a function that's going to give me those answers. And in this case, the sequence is 1 minus 1 over n squared. And what that does, or 1 over 2, yeah, 1/2 to the n. What that does is actually is going to give me the value of that and be able to do the calculations on it. So as I'm adding it closer and closer together, we can actually start seeing, if we added the first 25 of them, it gets really, really close to 1. So the sum of that infinite series is 1. And we can look at that, if we look at the function here, that n is the whole half, not they missed the parentheses there. So that 1/2 to the nth power, that's going to get closer and closer to 0. So 1 minus 0 is 1. Sometimes when we're looking at series, looking at the partial sums starts to give me a general idea of what's going on. So then I can actually use this sequence or the sequences rules to do it. Sometimes it doesn't, however. It doesn't always work that way. So if it's going closer and closer to a number, it's convergent. If the sum goes to infinity, or I can't come up with one, it's divergent. And that's how I'd write the limit of the sequence. And since it's going to n, that's going to be the partial sum. So I'm looking at the partial sums of it to do it, instead of going all the way out to infinity on the first shot. Okay, so if we look at this series, the series is a1 plus a2, and they give me equals 2 to the n over 3n plus 5. So I know that's my partial sum. That right there is a sequence. That's not the series. So the series is going to give me that value depending on whatever n value I'm plugging in and looking at. So when I'm looking at the limit of that sequence. And we do the same thing we just did in the last section, where we're actually just dividing them all by n. So we end up getting 2/3. So whatever series this is, doesn't make a difference what the function is. Since that's the sequence there, I know its limit is 2/3. So going all the way up to infinity, the biggest number it's going to add to is 2/3. This is an example of an arithmetic sequence because it's the addition of values all the way forward. We also have something known as a geometric series, which is something that's raised to a power. So this would be like the 5 to the nth power, where it's going to keep going up geometrically. So in a geometric series, there's actually certain rules that we can look at that helps me figure it out. In a geometric series, we want to figure out the common ratio. So they're going through and doing all these calculations out, and you're going to get to use this actual function. So in every geometric series, it's going to be a, whichever is the starting value. So there's your a. So that's your starting value right there. So whatever your S1 is going to be your a. And it's 1 minus the ratio raised to the nth power divided by 1 minus the ratio. So whatever that ratio value is, we're going to plug in there. And that's going to take whatever geometric series I have and give me the sequence that's produced from it. Now, in every geometric series, as long as the value is between if the value is between -1 and 1, it is convergent. If the value is less than -1 or bigger than 1, it is divergent. So that ratio, in essence, has to be a fraction, either positive or negative, to make it convergent. If it's anything bigger than 1 or negative 1, then it's going to be divergent. So let's look at a geometric series. So in this case, I've got 5 minus 10 to the third plus 29 minus 40 over 27. So to do this, the first thing I want to figure out is I need to figure out what my A is and what my R is. So my initial value is A. In this case, my A is 5. Now, I need to find my R. Now, my R is whatever value I'm going to multiply the 5 by to get the negative 10 over 3. And then it should be the same that I'm going to multiply that to get the 20 over 9. So to multiply 5 by something to get 10 over 3, I know I'm going to have it be negative, and I know I have to divide by 3 because that's not there. And 5 times 2 is going to give me 10. So my R is negative 2/3. You want to check a couple just to make sure that works. So if I take negative 10/3 divided by negative 2/3, it'd be positive 20 over 9. So I know that's my ratio for this. Now, if I remember, the function for this was the summation is going to always be A over 1 minus R. So there, right there, is going to be what the summation comes out to be. So that actually comes out to be my limit. So it's 5 over 1 minus negative 2/3. So that's 5 over 5/3. So this comes out to be 3. So the sum of this geometric series all the way down to the end is 3. So no matter how many values I have, going all the way to infinity, that one's never going to be bigger than 3. So this one converges to 3. This is another geometric series. This one we've got to do slightly different though. This one, the way they've got it set up, I don't have my A and my R. So we need to work on rearranging the function and basically do an algebra to rearrange this to actually come up to be something so that it's A times R to the nth power. So I need to have it look like that function there. So the first thing we're going to do is let's actually start breaking up that exponent. So I have 2 squared to the n. So that right there is no different than 4 to the nth power. The other thing is I always want it in terms of n, so I'm going to rewrite this as negative n minus 1. So if it's negative, that means that's going to go down the bottom. So that's 3 n minus 1. So now I have 4 to the nth power over 3 to the n minus 1 power. So now, how would I want to get, if I have the exponents the same on the top and the bottom, I can put those together. So if I change the top 4 times 4 n minus 1 over 3 n minus 1. By pulling out that 4, I in essence now have this one as n minus 1. Because remember, if I added those exponents together, because it's multiplication, same base, I would get back to the 4 to the n. So now those two are the same base, or the same exponent. So I can pull the 4 out in front, and I have 4/3 raised to the n minus 1 power. So now I have A and I have R. So when you're working with geometric series, the key piece to the whole thing is those exponent rules that you probably learned in algebra class a long time ago. Being able to manipulate that exponent rules to come up with an actual equation is going to be very, very helpful. Now, I don't actually have to do any calculations. The one I was asking is a convergent or divergent? The only question I need to know in that case is what is R? R in this case is 4/3. Since that 4/3 is bigger than 1, this function diverges. So in this case, it says find the sum of the series x to the n, or the summation of n from n to 0 of infinity of x to the n, where x is less than 1. So in this equation, I don't actually have a value for x, so I'm not going to be able to come up with an actual specific numerical answer, but I am going to be able to come up with a function. So we're going to do the exact same thing we did before. The key piece here, though, is I still need to figure out what a is and what r is. So a is my initial value, or my multiplication. In this case, it's just 1. There's nothing in front of that x. Now my r, in this case, is x, because that's what's raised to the power. Now we have to ask, is this function convergent or divergent? Because if it's divergent, there's no answer. Because it says the absolute value of x is less than 1, that means my r is less than 1. The absolute value of r is less than 1. Therefore, it is convergent. So now all I'm going to do is plug into my function for geometric equations. So it's 1 over 1 minus x. And that's all right, we're going to look at two more things. First thing is the harmonic series. We have seen the harmonic series before. The harmonic series is 1 over n. Now, what they were trying to show here is that 1 over n is divergent. Now, one of the things that we're going to look at a little bit later on is 1 over n squared, and we're going to see those things are a little bit different. So 1 over n is known as a harmonic series. It's 1, 1/2, 1/3, 1/4, and so on and so forth. We want to figure out, is this divergent or convergent? So for it to be divergent, that means the function's always got to be getting bigger and bigger. So how they do this is actually just as a set of partial sums. And what they do is, instead of looking at all the numbers between it, they pick very specific ones. They're actually picking the powers of 2. And what that allows me to do is it allows me to actually simplify the function down so I can do some simple calculations with it. So the first partial fraction is going to be s squared, or s2. So that means we're going to look at the first two values, 1 and 1/2. Now, if I look at the partial sum 4, I got 1, 1/2, 1/3, and 1/4. Now, I know that value right there is going to be bigger than 1, 1/2 plus 1/4 plus 1/4. Because all I did is I changed that 1/3 to 1/4. So I know this value right here is bigger than this value. This value right here is 2. So this value right here is 1.5. I know that my first partial fraction, the 2, is 1 and 1/2. And the fourth one is 2, or bigger than 2, because it was bigger than that value. If I look at the eighth one, my eighth partial fraction, if I add up all those, and you notice they break down the same way. They're saying this happened to be bigger than this one. They're just making them simpler, so I can just basically go back to dealing with 1/2. I know that my eighth partial fraction is going to be bigger than 2.5. I know my 16th partial fraction is going to be bigger than 3. So notice how these partial fractions are always getting bigger. And if I look at the 32nd one, that's going to be bigger than 3.5, and the 64th one's going to be bigger than 4. So I know that that function's always going to be bigger than 1 over n divided by 2. So it's always going to work out to be the fact that that number is getting bigger and bigger and bigger and never smaller. So therefore, it diverges. The harmonic series is going to be probably one of the more important ones later on, because one of the rules that we're going to look at when we start doing some calculations with this is a comparison test. And if I can compare it to the harmonic series, I know it automatically diverges, so it does save me a lot of work later on. So if the series a to the n is convergent, then the limit of the actual values in it has to be 0. So if my series is convergent, I know my limit of the actual sequence has to be 0. So that means as I'm adding the numbers, as the numbers are adding to it, those numbers have to be getting smaller and smaller. Because if I'm adding a bigger and bigger number, or adding any number to it, it's going to go to infinity. So when we're looking at the series, if I look at the sequence of values, the sequence limit has to be 0. Not, then we have to look at some other information. So if the series is convergent, I know my limit of the series, or the sequence, is 0. The opposite, that's not true. If I know the limit of the sequence goes to 0, I do not know if it's convergent. And a perfect example of this is what we just looked at, was the harmonic series. If I look at that one, those values are getting infinitely small. They're going to 0. So the limit of the harmonic series is 0. However, we just showed that it is not convergent. The last one we're going to look at is known as the test for divergence. The test for divergence comes from what I was just talking about. Is if I know my limit of the sequence does not exist or does not equal 0, then I do know that the series is divergent. So if this doesn't exist or isn't 0, then it's divergent. Kind of comes from this one. I know it's convergent if my limit equals 0. If that's not 0, then that right there has to be divergent. I think I'm going to end there. So does anybody have any questions? Okay. Two things. One, everybody make sure you go sign up for XYZ homework. On XYZ homework, there is an ebook that goes along. It's not the same book that you have currently. The book you have currently will work completely well. You can do the homework assignments in that book as well. But XYZ homework has videos and examples and PowerPoints and problems for each of the sections that we're looking at in this book. I've made sure that the chapters go right along with it. So the chapters in the ebook the numbers might be different, but you'll notice the actual assignments and everything else do match up with our book exactly. So you can practice those things. If you have any questions, any problems, any suggestions on what we can do with this going forward, please email me and message me and let me know. I'm always looking for little ways. This is the first time I've done this in a long time, and I'm pretty sure this is the first time most of you have done this as you're signing up for traditional school, not online school. So we're going to get through this together. Little by little, we'll make some changes, and it'll get better as we go. So we're going to end here. If you do have any questions, feel free to email me. If you have not sent me your test already, please make sure you do that as soon as possible. If there's some other extenuating circumstance, just let me know, and we'll take care of those things as we go. I will see you on Thursday, same time, same place.